In this lesson, we're going to introduce you to sequences, and then later on, we're going to be talking about series. Let's go ahead and define what a sequence is. A sequence is a set of numbers with a particular order or pattern, and we call each number in the sequence a term. And now a finite sequence, the word finite means that you can actually count it. A finite sequence is a sequence with a limited number of terms. An example of that, if you had the sequence 1, 2, 3, 4, 5, notice the pattern there, but if it stops and it doesn't continue on forever, that's called a finite sequence. So the opposite of that would be an infinite sequence. An infinite sequence is a sequence with unlimited terms, so it has no ending. And we know what infinite means, and that's exactly what we see with an infinite sequence. And an example of that would be 0, 1, 2, 3, 4, dot, dot, dot. And you have that dot that shows you that goes on forever. That would be the sequence of all the whole numbers. That would be an infinite sequence. Now let's talk about term notation. The first term in a sequence is denoted A with a little 1 next to it. Now this could be, if this is your sequence A, this could be B1, B2, or excuse me, B1, C1, D1. But the little 1 next to it means that's the first term in the sequence. So in our previous sequences, here's our A1 and here's our A1. Each subsequent term is denoted A sub n, A with a little n, to where the n is the term number in the sequence. So A with a little 2 would be the second term. A with a little 3 would be the third term. So in the given sequence here, identify the following values. What is A of 1? That's your first term. It's a 1. What is A of 4? That's 1, 2, 3, the fourth term, which is 13. What would be A of 9? What would be A of 12? Well, we'd have to continue this sequence on and on and on. So if we keep going, looks like we're adding 4 each time, so we'd have 21, 25, 29, 33, 37, 41, and 45. Let's see if that's enough terms. We need the ninth one. That's 1, 2, 3, 4, 5, 6, 7, 8. Our ninth term would be 33. Our 10th, 11th, 12th term would be 45. Now let's look at sequences as a function, because we've talked about functions, the whole f of x stuff before. A sequence can be a function since each term value is paired with exactly one term number. There's not two different term ones, or there's not two different A2s and A3s and A4s. Your third term is one number, so therefore this is a function. The domain is the set of all the term numbers. The first term, the second term, the third term, the fourth term, that's your domain. The range would be the term value. What is the value of the first term? What is the value of the second term? In an infinite set, the domain is the set of all natural numbers. Because we know our natural numbers are 1, 2, 3, 4, 5. It's the counting number. So therefore, the domain would be all of those natural numbers. Now let's talk about what we mean by a recursive formula. The recursive formula is a rule in which one or more previous terms are used to generate the next term. Now, I could give you a verbal example of this if I say each number in a sequence is 3 more than the one before it, or each number in a sequence is 5 times the one before it. Notice that I'm comparing each number to the ones before it. Now, a Fibonacci sequence, which is what we're going to talk about next, actually defines the values of a sequence based on the two values before it. And here's what the Fibonacci sequence looks like. It's 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, dot, dot, dot. And it is an infinite sequence. Now, where did I get those values? In this sequence, A of 1 and A of 2 is 0 and 1. Then for each subsequent term, each term in the sequence is equal to the term before it, A sub n minus 1, that would be the term before A sub n, plus A of n minus 2. So what this means is each term in the sequence is equal to the term before, because think about it. What if n was 5? Then 5 minus 1 would be 4, and 5 minus 2 would be 3. So A sub 5 would be A sub 4 plus A sub 3. A sub 6 would be A sub 5 plus A sub 4. A sub 10 would be A sub 9 plus A sub 8. each term in the sequence is equal to the sum of the previous two. This term in the sequence is equal to the sum of the previous two. Again, this is an example of a recursive formula. Now let's work some examples. It says find the first 5 terms of each sequence. Well, to give you the first one, ace of 1 is 14. Let me write that down. Now this says each term in the sequence is equal to the term before it. That's what that whole ace of n minus 1. So how do I find ace of 2? Well, n is 2, so therefore if this n is 2 also, that's 2 minus 1, which is 1. So ace of 2 would be ace of 1 plus 9. So here's ace of 1, add 9 to that, ace of 2 would be 23. Ace of 3, if n was 3, would be ace of 2 plus 9. So we're going to add 2 to that, that would be 32. Well, how do I find ace of 4? Well, you would find the ace of n minus 1, which would be ace of 3 plus 9. So this simply means each term in the sequence, that's what ace of n is, each term in the sequence is equal to the term before it plus 9. So 41, 50, and we could go on and on from there, but that's the first 5 terms in the sequence. The first term here is 6, and it says each term in the sequence is equal to 2 times the previous term minus 5. So to find ace of 2, we've got ace of 1. To find ace of 2, we're going to do 2 times ace of 1 minus 5. So therefore, here's my ace of 1. I'm going to plug in 6. 2 times 6 is 12, minus 5 is 7. Now, how do I find the next term? Then I plug in the place of here the previous term, which is 7. 2 times 7 minus 5. That's 14 minus 5, which is 9. How do I find the next term? I plug in 9 here. 2 times 9 minus 5. That's 18 minus 5, which is 13. And then how do I find the next term? I plug in 13 here. That's 26 minus 5, which is 21. And that would be the first 5 terms in the sequence. Now, what does this whole for n is greater than or equal to 2 mean? Well, that means to find, here's your n value. For all values 2 and above, how do you find the second term, the third term, the fourth term? Well, what about n equals 1? Well, we're given n equals 1. So for every other value greater than 2, to find a2, to find a of 3, to find a of 4, you're going to use this formula. So that's what that means. Okay, here, your first term is equal to 354. To find the next term, you're going to take the first term, the term before it, you're going to add 6 and divide by 3. So if we add 6, that's 360, and divide by 3, you get 120. Well, how do you find the next term? You take that term, you add 6 and divide by 3. So it'd be 126 divided by 3, that'd be 42. Well, how do you find the next term? You add 6, you divide by 3. 48 divided by 3 is 16. And then to find the last term, you're going to add 6 and divide by 3 again. That's going to be 16 plus 6, which is 22, and we've got to divide that by 3. Since it's not divisible, we can just leave it as 22 thirds. Number 4. Now this one's a little bit different. We're going to say ace of 1, our first term is 3, our second term is 4. To find the next term in the sequence, to find a of 3, you're going to do a of 3 minus 1, which would be a of 2, times a of 3 minus 2, which is 1. So to find the third term, you're going to multiply the second and first term. So you're going to do 3 times 4 is 12. Well, how do you find the fourth term? A of 4, if n is 4, you're going to do 4 minus 1 and 4 minus 2. That would be a of 3 times a of 2. So you'd multiply these two terms together and get 48. Well, how do you find the next term? You multiply the two previous. So this says each term is equal to the product of the previous two. So when we do 12 times 48, we get 576, which would be the fifth term in the sequence. Okay, number 5. Starting with number 5, we have some new directions. It says write a rule for each sequence, then give the next 3 terms. So let's see if we can figure out the recursive formula for this sequence. Let's start out with something simple. 4 to 11. Could we add 7 each time? Well, if we added 7 again, we don't get 32, so we're going to have to scratch that. So then we go to maybe a multiplication or division, and I know there's nothing I can multiply 4 by to give me 11. However, if I multiplied by 3, it would give me 12, which is a little bit off, but it is close. So let's check that times 3. If I multiply 11 times 3, I get 33, which is still really close, but just one off. 32 times 3 is 96, so I think we're on the right track. Each term in this sequence is going to equal 3 times the term before it. But again, if we do that, 4 times 3 is 12. That's too high. So then we're going to subtract 1 from the answer, and that's going to give us the next term in the sequence. And you can check that here. 11 times 3 is 33. Take 1 from it, gives you 32. 32 times 3 is 96. Take 1 from it, gives you 95. So that does check out. Now the next, I believe it says give the next 3 terms in the sequence. We can just come out here and list this. We're going to take 284. Again, we're going to multiply it by 3. That's going to be, let's see, 852, then subtract 1 gives you 851. Do it again, multiply that by 3, and then subtract 1, and you get 2,552. Take that number, multiply it by 3, and then subtract 1, and you should get 7,655, and that's your next 3 terms. Next one. 160, 40, 30, 25. Okay, let's try again a basic one. Are we subtracting 40 each time? Because 100 down to minus 40 gives me that 60. But if we try that again, now we get 20 instead of 40. So that it's not simple. So then we go to a multiplication or division pattern. Since we are decreasing, we're either going to be dividing or multiplying by a fraction. That's the only way that we can decrease if we're multiplying or dividing. So let's take 100 and think about some things that we're going to multiply or divide by. That's going to give me something close to 60. Well, I know if I divided by 2, it would give me 50. So that's a little bit too low, but it's close. Well, if I took this one divided by 2, it would give me 30. If I took this divided by 2, it would give me 20. Took this divided by 2, it would give me 15. Notice what I'm getting is close to what I need. 50 is 10 low. 30 is 10 low. 20 is 10 low. Okay, so we're on the right track. Each term in the sequence will equal the term before it, divided by 2. And then in order to get back from this 50 up to a 60 or the 30 up to the 40, we will add 10 to that. So each term is equal to the previous term divided by 2, and then add 10 to it. So we got to take 25, we got to divide that by 2, which gives me 12.5, and then add 2 to it. That would give me a 22.5 as the next term. Take that, divide by 2 would give me 11.25. So that would be 21.25 when I added 2 to it. Take that, divide it by 2 again, and then divide it by 2, and then add 10 to it. And my next term in my sequence would be 20.625. And there's the next 3 terms. Okay, next up, we're going to talk about explicit formulas. Let me zoom out so we can define this. By definition, here's what we mean by an explicit formula. It's a rule in which the nth term is defined as a function of n. Now, this is great. Previous terms unnecessary. So, let's look at our first example. A sub n equals 7 times n minus 3. Notice there's no a sub n minus 1. We do not need the previous term to find any term. Notice if on these problems, if I said on number 5, find the 100th term in the sequence, we're going to be working a while because we found we were given 1, 2, 3, 4, 5, and we found 6, 7, and 8. Well, we would have to find number 99 in order to find number 100. You had to use the previous term to find the next one. Well, explicit formulas work differently. If I need to find the 100th term, this thing is defined as a function of n to where n is the term number. So if I need to find the 100th term, no problem. And I'll show you why. Number 7 says to find the first 5 terms in the sequence. And notice we don't even have a sub 1 given. We can find a sub 1. How do we find a sub 1? N is the term number you're looking for. So in order to find a sub 1, we simply do 7 times 1 minus 3. Take out n and plug in whatever term you're looking for. And that's going to be a negative 14. To find a sub 2, we're going to do 7 times 2 minus 3, which would be 7 times negative 1, which is negative 7. Find a sub 3, we're going to do 7 times 3 minus 3, which would be 7 times 0, which is 0. A sub 4 will be 7 times 1, which is 7. And then a sub 5 would be 7 times 2, which is 14. So your terms are negative 14, negative 7, 0, 7, 14, dot, dot, dot. That's the first 5 terms. Now, could we find the next one, ace of 6, by looking at this pattern? Yes. Could we use the previous terms now and kind of define this recursively to find the next ones? Yes. 7, 14, 21, 28. We see that these are simply multiples of 7 here, right? Number 8. Again, what if I needed the 100th term? You plug in 100 there. That's it. So let's go ahead and find the first 5 terms. A of 1 would be 1/3 raised to the 1 plus 1 power. That's going to be 1/3 to the second power, which is 1/9. Find A of 2. We're going to do 1/3 raised to the 2 plus 1 power, which will be 1/3 to the third, which is 1/3 times 1/3 times 1/3, which is 1/27. So what did we do there? We pretty much multiplied by another 1/3. So you can kind of see the recursive formula coming out. 1/3 to find the third term, that'd be 3 plus 1, or 1/3 to the fourth power, which is 1/81. And again, you can finish by plugging in a 4 and plugging in a 5, a 5, but you're going to get 1/243 and 1/729 for your next 2 terms. Number 9, -4n squared. A1 would be -4 times 1 squared. Make sure we square before we multiply by -4. That's going to be a -4. A of 2 is going to be -4 times 2 squared, which is -4 times 4, which is -16. A of 3 would be -4 times 3 squared, which would be -4 times 9, which is a -36. A4 would be -4 times 4 squared, which would be -4 times 16 is a -64. And then A of 5 would be -4 times 5 squared, which is -4 times 25, which is -100. There's your first 5 terms in the sequence. Number 10. Now you could multiply this out, actually distribute there, but we'll just use it as is. Ace of 1 would be 2 times 1, which would be 2 times 1 plus 5. That's going to be a 12. Ace of 2 is going to be 2 times 2 is 4 times 2 plus 5, which is 7. 4 times 7 is 28. Ace of 3 would be 6 times 8, which would be 48. Ace of 4 would be plug in a 4 and 4. That'd be an 8 times 9, which is 72. And then finally, ace of 5 would be 10 times 10, which is 100. There's your first 5 terms of the sequence. Number 11. Ace of 1 would be -2 to the 1 minus 1 power, which would be 0. Anything to the 0 power is 1. The second term in the sequence would be -2 to the 2 minus 1, which would be -2 to the first, which is -2. And you're going to see that these flip back and forth from negative to positive because of the odd and even powers. The third term is 3 minus 1 power, which would be the second power. That'd be 4. Then you can finish that out. A of 4 and A of 5 would be a -8 and a +16. If you see the pattern, you can actually go ahead and find the next terms. Instead of plugging in, you can just see and just write down the next terms in that sequence. A of 1 here would be 1 minus 4, which is -3 to the second, which would be 9. A of 2 would be 2 minus 4, which would be -2 to the second, which would be 4. A of 3 would be 3 minus 4, which is -1 to the second, which would be 1. And that's all. That's some perfect squares there, 9, 4, 1. I think we're going to get 0 to the second, on the next one, which would be a 0. And then A of 5 would be 5 minus 4, which would be a 1, +1 to the second, which is back 1. And that's kind of like a quadratic. You can see like a parabola happening there, 9, 4, 1, 0, 1. And I believe the next 2 terms would be a 4 and a 9. And then that would be a parabolic type sequence. Okay, next up, directions. Write a rule for each sequence, then give the next 3 terms. So we've got to somehow, this is the first term in the sequence, the second term, the third term, and so on and so forth. We have to somehow relate these numbers to this. Okay, how can we use 1 to give me 7? Well, we could add 8. Are we going to add 8 to all these to get our numbers up here? No. But it is, well, it's not even close, right? Or excuse me, subtract 8. but we're semi-close there. Subtracting 8 from 2 would give you a -6. Subtract 8 from 3 gives me a -5. So kind of close. So we're going to have to try something else here. Now, one thing I do notice, look at this. I just saw this. We're going down 2 each time. So we've got an extra, I guess you could say -2. Like, think of it like this. We're going to have to look at this as kind of like a t-table here of ends and ace of ends. My first term is -7. My second term, -9. My third term, -11, and so on and so forth. So could I multiply something by these values and then add it to my other values in order to obtain them is what we're looking for here. So let's look at that. If I were in order to find my ace of n, if I were to multiply something by this value, well, let's try to multiply some values. Let's try maybe -6 times my n value. And then how would I get the -7 from that? Well, I would subtract 1. Well, let's see if it holds for the next one. -6 times 2 is -12. -1, no, that's a little bit too low. So let's try something different. Let's multiply maybe -5 times my n values. If I were to multiply -5 times this, I get -5. And then if I were to subtract 2 more, that'd give me my -7. Let's check it for the second one. -5 times my 2 would be a -10. And then when you subtract 2 more, that would give me a -12. So that doesn't work. So you can see already the trouble with trying to find an explicit rule is not very easy. Sometimes you might be multiplying by something and then adding. Sometimes you might be squaring and then adding. Sometimes you might be dividing. Sometimes you might just be adding. So you can continue on, okay, -2. What if I were to multiply -2 times 1? That gives me -2. If I were to subtract 5 more from it, I get -7. Well, check it here. -2 times 2 would be a -4. Subtract 5 more, you get a -9. -2 times 3 is -6. Subtract 5 more gives me -11. So there's my rule. Now to find the next 3 terms, plug in 6. And a of 6 would be -2 times 6 is -12 minus 5, which is -17. Ace of 7 would be -2 times 7 is -14 minus 5, which is -19. And again, you just see that we're going down 2 each time, so the next one would be -21. So there's your next 3 terms. Now the next one, 3, 6, 11, again, you can try to create yourself a little t-table. My terms, my first term, second term, third term, fourth term are 3, 6, 11, and 18. And remember a while ago, I told you sometimes you might multiply by something and add something to it, like maybe you're going to multiply 1 by 3. Well, it looks good here. 2 times 3 is 6, but 3 times 3 is not 11. So it worked for the first 2, but it's got to work for the entire sequence. Well, could we maybe multiply by 2 and then add something to it? So maybe ace of n would be 2 times n, and then add 1 to it. 2 times 1 is 2 plus 1 is 3. 2 times 2 is 4 plus 1 is 5, not 6. So that doesn't check out either. Sometimes you might have to square your n term. Maybe it's something like n squared. When you square 1, you get 1, and then you can add 2 to that. It gives you 3. Square 2, you get 4. Add 2 to that, you get 6. Square 3, you get 9. Add 2 to that, you would get 11. So this is checking out square 4 gives you 16. Add 2 gives you 18. That is your rule. So therefore, we've got 5 terms there. Let's find a 6, 7, and 8. And again, to do that, the rule is we are now going to square my n and then add 2. So it'd be 36 plus 2 is 38. 49 plus 2 is 51. 64 plus 2 is 66. And there's the next 3 terms in your sequence. So that was tricky, and these are difficult. But again, as we proceed, we're going to find easier methods for doing this. We're just, I guess, just showing you how hard this is without other methods. Here, notice I'm going to have to be dividing by 2 somewhere. So let's do this. Let's look at, I know that ace of n is maybe n divided by 2. Let's see, if the first term, let's do my t-table again, n and ace of n. My first term is a 2, so therefore if I divide 1 by 2, I don't get 2. If I divide 2 by 2, I definitely don't get 5 halves. But let's focus on this one to try to get my rule. If I take this n over 2, let's see, I've already got my 2 on bottom. What if I add a 3 to the top? Since I know that n is 2, and I leave it as n plus 3 over 2. Well, does that work out for, let's definitely check 4 and 7 over 2. That'd be an easy one to check. If you put a 4 right here, do you get 7 over 2? Sure you do. When you put a 3 right there, 3 plus 3 is 6. 6 over 2 is 3, which is what I wanted my third term to be, and that is your rule. The fifth term, fifth, sixth, and seventh term, let's see, to plug in, or excuse me, sixth, seventh, and eighth terms, plug in 6, you're going to get 9 over 2. Plug in 7, you're going to get 10 over 2. Plug in 8, you're going to get 11 over 2. So there's your next 3 terms in the sequence. Now this one's probably the easiest one of all the ones that we've worked. N and a sub n. The first term is 1. The second term is the square root of 2. The third term is the square root of 3. The fourth term is the square root of 4. So the fifth term is root 5. I bet the root 6 term is root 6, root 7, and root 8 would be the next 3 terms. So each term in the sequence is equal to the square root of n, where if n is 1, the first term is root 1, which is 1. We could clean that up. Second term, root 2, leave it. Root 3, leave it. Root 4 is 2, so that does check out then.